Right, welcome to today's lecture where we're going to be starting our conversation on electric currents. So we're going to move away a little bit from just stationary charges because, while that does exist, how we personally use electricity more often is going to be related to the electric current, which participates in the electricity inside of our home. So we're going to be spending a bit of time on this. So before we get into electric currents, we need to look at what we talked about last time. So last time we introduced the electric potential, which was given the variable V, and it's the potential energy, the electric potential energy per charge. And there's kind of two ways we're going to be looking at potential. We're going to look at how the potential at a bunch of different points adds up together, and we can also look at the potential difference, in which it's just the change of potential between two different points. And either way, with how we're going to be looking at potential is a scalar. So we need to make sure that we account for the charge. Here we have our equation for the potential of a point charge. So it's K, so it's that same constant we've been seeing multiple times throughout the semester, times our charge. Here it's going to be important to include the negative or the positive sign for our charge to indicate the correct sign for the potential, divided by the distance. So this is going to give us our equation for the potential of a point charge. And then we briefly looked at the equal potential lines, which are lines that represent, so everywhere on this line, whatever it happens to look like, that means that the potential has the same value at all of these locations. So the reason we need to talk about potential is it's actually going to be really important for the motion of our electrons inside of a circuit. And so what we're going to be doing today is building up some of the concepts for circuits so we can start building into circuits and a little bit with how those behave. So we're going to start building into that today. And so in order to look at that, we're going to look at the electric battery. That's going to be in our first video. In the second video, we're going to be looking at electric current. And the third video is going to discuss Ohm's law as well as resistivity, because they go hand in hand with each other. So in this first video, when we're discussing the battery, we are not going to be discussing every single aspect that is happening inside of the battery. You might have seen it before in your chemistry class where you talked about the actual chemical reactions happening. That is a chemistry aspect of the battery. In physics, we don't necessarily care about the same things, so we're going to look at it in a different view than what you may have seen before. So we're going to be ignoring the history of the battery. It's there in the textbook if you're interested, but we're just going to kind of skip to how physics views it. So the electric battery is defined as a transformation or something that transforms chemical energy into electric energy. So we are taking a chemical reaction that's happening. Again, we're not going to be focusing on the actual chemical reactions, and that's going to allow for some type of electrical energy to be created instead. So we still have a conservation of energy happening inside of our battery, except for it's going to be chemical and electric energy, which both happen to be potential energies. So some of the terminology that we're going to be seeing is the electrode. And so inside of a battery, the electrodes are going to be either two dissimilar metals, or you can have a metal with carbon. We also are going to have the electrolyte, which is going to be a solution or paste that allows electrons to flow from one location to another. So a very important part of electricity is the motion of electrons. So if a battery is part of your circuit, which primarily with what we'll be doing as we build up circuits to look at electricity, we're going to have batteries in them. So we need to have some sort of electron flow inside of the battery. So this is kind of a common, simplified version of a battery. And this is going to be the one we focus on primarily in this class. However, again, we're talking about batteries now. We're not focusing on the chemical reactions. We're just like, hey, this is how they work and this is why it's important. So we have a positive, here we have a zinc carbon battery. So this carbon electrode and this zinc electrode are our metal with carbon. And these would be connected to wires going out into our circuit. We then have our electrolyte, which corresponds to our sulfuric acid. And a chemical reaction is going to occur between our electrodes and our sulfuric acid that results in a flow of electrons. So you'll notice here that we already have a plus terminal and a minus terminal. That's going to be based on our chemical reaction that we'll very briefly look at in the next slide. But we have two stationary, in this case they're rods, things with positive and negative charges. So that means that there's going to be a force between the positive and negative charge. There's an electric field between our positive and negative charge, and there's going to be a potential between the two, or a potential difference in reality between the two sides of the battery. And it's this potential difference that's important. So this is, again, what we're going to be focusing on right now for the electric battery. There are other types outside of a zinc carbon sulfuric acid battery. This is just the one the textbook is going to be using. So we want to kind of focus a little bit more on how it works and how we know which one's positive and which one is negative. So sulfuric acid is going to dissolve the zinc electrode. There's going to be a chemical reaction that's able to interact with the zinc. And what's going to happen is the zinc is going to get dissolved. However, the electrons, two of the electrons, are going to stay in the electrode itself. And an ion of zinc is going to go into the sulfuric acid. And so the sulfuric acid is going to become positively charged. And what it can do is, because now the acid is positively charged, it wants to be neutral. It's in contact with our carbon electrode. It's going to start pulling electrons from the carbon electrode, which is going to force it to be positive. And so if this starts to get connected to things, the constant pull of electrons through the carbon electrode is going to be what causes our current to flow in our circuit. So this change, this attraction of positives and negative charges to each other results in a flow of our electrons. And basically this is going to go on until one of the electrodes is used up. From my understanding of varying types of batteries, that's typically going to be if you have a carbon metal one, it'll typically be the metal. And metal, it's just going to be whichever one I think kind of like changes the most. So this is how the electric battery works. So again, not all batteries are explicitly this type of battery, but it's the basic principle in which we're going to be using batteries in this class. We're not going to actually care about what exactly is happening in the battery. Tends to be a little bit more on the chemistry side, but it's important to look at. And so we can take the electric battery and we can actually put a lot of batteries together. So we need to figure out what happens with that. So if you've ever, some remote controls or, some graphing calculators, if you have to use batteries, you have batteries lined up where they're flipped in opposite directions from each other. That is, one way in which we connect multiple batteries to power the same object, in that case, your graphing calculator. Some remote controls use that as well. If you look at flashlights, some larger flashlights, you can put two batteries in together and they work together to power your flashlight. So because we have that positive and that a negative electrode, we had a potential. So if we take our battery, which now we're representing it in a slightly different manner, so this is what a normal battery looks more like, not an open, container of acid. We have a positive terminal and a negative terminal. And inside we have, in this case, it's an electrolyte paste. It's not acid. We've tried to move away from acids as much as possible. So we can literally just stack the two batteries on top of each other, and that's going to let us add the potentials together for what we look at in terms of a circuit. Now we'll come back to this when we start building into circuits a little bit more on how that's represented, but we can, put them together and we can add the potentials. So if you have two 9-volt batteries and you line them up like this, you add the two potentials, 9 plus 9 would be 18. But again, we'll come back to adding up our potentials a little bit later when we start building up circuits a lot more in the next couple of lectures. I just want to kind of go over the lithium-ion battery. So this is, this is a really rough schematic of what's happening with the lithium-ion battery. So one of the rechargeable batteries. So these are used in quite a few different locations. Laptops, some cell phones, cars, they all use the same type of principle. So with a lithium-ion battery, we have our lithium ions, and they actually move back and forth between the anode and the cathode inside of our battery. So the electrons move, the ions then move, and we have our current. So if you're discharging, the lithium ions go from the anode to the cathode, and charging, we're able to shove the ions back into the anode side of our battery. And so what happens in this case is we're not using up our lithium ions. Instead, what we're using up is the structural integrity of the anode and the cathode. Because as time goes on, the constant changes between having and not having the ions is going to make it so that maybe you can't hold as many on one side as you used to be able to do. So this is why over time, your charge capacity on your rechargeable devices goes down. The structural integrity of your anode and your cathode decrease with use. So of the two batteries we've looked at, those are just a couple of different types. Here we have some of the bigger battery types that you might see in kind of a more day-to-day situation. If you look at the European Union Recycle program, they tell you kind of how you could go about recycling the common types of batteries. I know a lot of people say don't look at Wikipedia, but I mean, it's a really good place to start looking at stuff. So, I went to Wikipedia and I put in types of batteries, and these are just all the different types of batteries that you can look at. So on the right here are, sorting the other two columns by application, but, I know this list isn't very legible, but it's just a huge list of all the different types of batteries that we have. And, this is something that is constantly changing. There's still research being done on batteries, especially our rechargeable batteries. So it's just kind of this interesting place where we're still developing types of batteries. They all follow the same general ideas of being able to have a potential difference between the two different sides, causing electrons to flow. So even though, there's this huge list, the same general principle holds true. It's just how it does that is going to be different. All right, so this is going to wrap it up for the first video. Make sure to watch the next two videos as well.